Good day. I'm David Gabriel Feliciano, and this is my final completion presentation for a transmission media and antenna systems lecture and lab. So, first and foremost, what is transmission lines and antenna systems? Um, it is a system of conductors having a precise geometry and arrangement that is used to transfer power from source to load within minimum loss. It means of conveying information from one point to another. The conductive connections between system elements which carry signal power. So, antenna and transmission line irrigation analogy. So first, irrigation requires a hose to transport the water to the sprinkler, and transmission line, a sprinkler to direct the water to the specific area we want to irrigate the antenna. Antenna, it is a structure associated with the region of transition from a guided wave to a free space wave radiating a radio frequency energy. So transmission line, it is a metallic device used to guide radio frequency energy from one point to another, as I said before. It is also the line device used to guide the radio frequency energy from one point to another. Example, coaxial cable and bifilar line and waveguide. Every transmission line will attenuate the signal. The simplest transmission line is the bifilar line, formed by two parallel conductors separated by air or an insulator, and it will carry the RF signal from the source to the other end. There can be an alternating current even in an open-ended transmission line, since the electrons will flow back and forth every half of the cycle. The electric field at a distant point created by each of the currents will be the one of the same magnitude but in opposite direction and will therefore cancel. The cancellation of two electric fields is included in transmission line. So bent ends transmission line, if we bend one extreme upward and the other downward, the currents will now flow upward in both segments and the electric fields will create and will reinforce. The resulting electric field will cause a current to flow in any conductor present there. So we have now an antenna. This is what a bent end looks like as an electromagnetic force. So the bend at the end of the antenna follows the current where it is bent. So irrigation system components. So as we can see here, a central access point is basically the wireless equivalent to of a LAN hub. It is a small box with one or more aerials that uses a connector to attach it to the rest of your wired LAN. Access points receive and transmit data from and to all the wireless devices in their area. They can handle many different connections between different devices, all talking to each other at once. But the more devices you have working with an access point, the slower they will operate. You may need more than one access point to cover a building depending on its range and the composition of any walls or floors between the access point and the wireless network card. So this is wireless system components. So as we can see here, here is the simplest diagram when it comes to the wireless component systems. Here we see that the radio is connected to the antenna by coaxial cables. So there are many types of transmission lines. Um, the first one is the differential or balance line, where neither conductor is grounded. Um, two wire open lines or parallel lines have uses such as power lines, rural telephone lines, and telegraph lines. This type of line has a high radiation losses and is subjected to noise pickup. Twin lead Twin lead has parallel lines. It is the most often used to connect televisions to their antennas. And twisted pair consists of two insulated wires twisted together. This line has high insulation loss. And a shielded pair has parallel conductors separated by a solid dielectric and surrounded by copper braided tubing. The conductors are balanced to the ground. The next one is this single-ended or unbalanced line. Um, where one conductor is grounded, the rigid coaxial line contains two concentric conductors insulated from each other by spacers. Some rigid coaxial lines are pressurized with an inert gas to prevent moisture from entering. High frequency losses are less than with other lines. So the flexible coaxial lines, um, it is also consists of a flexible inner conductor and a concentric outer conductor of metal braid. The two are separated by a continuous insulating material. The common losses in a transmission line are the first one is copper losses. It can result from power loss, and in the form of heat or skin effect, these losses decreases the conductivity of a line. The next one is the dielectric losses. It is caused by heating the dielectric material between conductors, taking power from the source. Um, the next one is the radiation and induction losses. It is also caused by part of electromagnetic fields of a conductor being dissipated into space or nearby objects. So basically, a transmission line is electrically long. If its physical length is greater than the common wire that we use, the line is short. And there are theoretical properties includes in this topic. The first one is the Lamb constants. It is a theoretical property of a transmission line that are lumped into a single component. The next one is the distributed constants. It is a constant of inductance, capacitance, and resistance that are distributed along the transmission line. And the last one is the leakage current. It flows between the wires of a transmission line through the dielectric. The dielectric will act as a resistor. So, coaxial cable. Coax is a type of electrical cable consisting of an inner conductor surrounded by a concentric conducting shield with two separated by dielectric. Many coaxial cables also have a protective outer sheath or jacket. The term coaxial refers to the inner conductor and the outer shield sharing a geometric axis. It is also a type of transmission line used to carry high frequency electrical signals with low losses. It is also used in such applications that telephone trunk lines, broadband internet networking cables, high-speed computer data buses, cable television signals, and connecting radio transmitters and receivers to their antennas. It differs from other shielded cables because the dimension of the cable and connectors are controlled to give a precise, constant conductor spacing and which is needed for it to function efficient as a transmission line. So the loss or the attenuation of a coaxial cable depends on the construction of the cable and the operating frequency. The total amount of loss is proportional to the length of the cable. So these are the types of cable and attenuation. So as we can see here, RG58, the diameter of RG58 is 4.95 millimeter, and the attenuation at 2.4 gigahertz is 0.846 decibels per meter, and the attenuation at 5.3 gigahertz is 1.472 decibels per meters. The next one is the RG213 type of cable. Its diameter is 10.29 millimeter, and its attenuation at 2.4 gigahertz is 0.475 decibels per meters, and its attenuation at 5.3 gigahertz is 0.829 decibels per meters. So in the next one, the LMR 400 cable type, its diameter is as the same as RG213 at 10.29 millimeters also, and the attenuation at the 2.4 gigahertz is 0.217 decibels per meter, and the attenuation at 5.3 gigahertz is 0.341 decibels per meter. The next one is the LDF450A cable type. Its diameter is 16 millimeters, and the attenuation at 2.4 gigahertz is 0.118 decibels per meter, and the attenuation at 5.3 gigahertz is 0.187 decibels per meter. So impedance. So in this section, radio wave propagation is connected. So here, we will discuss the different type of frequencies. The first one is the ELF, or what we call extremely low frequency. It ranges 30 hertz to 300 hertz. The next one is the VLF, or the very low frequency. It ranges 3 kilohertz to 30 kilohertz. Radio waves at these frequencies are very reliable for long-range communications, because the attenuation of the ground waves is very small and the sky wave reflection is good. The radio navigation, aeronautical communications, and maritime mobile communications is using this process. The next one is the LF, or low frequency. It ranges 30 kilohertz up to 300 kilohertz. Attenuation of ground waves here is higher than VLF, or what we call very low frequency. Is because sky absorption begins to be a factor, especially at the higher end of this band. It is also used by the process of radio navigation, aeronautical communications, and maritime mobile communications. The next one is the MF, or what we call medium frequency. So this stage of frequency, it ranges 300 kilohertz up to 3 megahertz. This region includes the standard AM broadcast band, in which it is possible to obtain reliable ground wave coverage up to up to 100 miles from the transmitting antenna. Um, it is used by the process of amateur communications and the maritime and aeronautical communications also. The next one is HF, or what we call the high frequency. It ranges 3 megahertz up to 30 megahertz. Skywave propagation is the only reliable means of communicating over long distances, especially at up the upper band of this end. Well, it is used by shortwave broadcast pointing, point-to-point communications, and land, maritime, and aeronautical communications also. So the next one is the VHF, or what we call very high frequency. It ranges 30 megahertz and up to 300 megahertz. This region also includes the commercial FM, and very high frequency TV bands, television bands. So the line of sight is the principal means of communication. It is also used by shortwave broadcasting, point-to-point communications, and land, and maritime and aeronautical communications also. The next one is the UHF, or what we call the ultra high frequency. So it ranges 300 megahertz up to 3 gigahertz. In the line of sight of propagation, it is possible beyond to optical horizon due to increasing refraction effects on Earth's atmosphere. It is also used by TV broadcasting, radio astronomy, aeronautical and land mobile communications, and satellite TV communications. So the last one is the SHF, or what we call super high frequency. It is the highest it is the highest stage of the frequency because it ranges 3 gigahertz up to 30 gigahertz. So it represents the upper limit of frequencies that have any practical use in radio wave communication, using standard method of generating and transmitting signals. It is used by the process of microwave relays, satellite, and the exploratory communications. So free space is also related in radio wave propagations. So what is free space? It is an idealized wave environment where there are no other transverse electromagnetic, or what we call TEM, no gravity, no obstructions, no atmosphere, no celestial events, no terrestrial events, no electrical noise, and no 43 observers. In short, the wave environment is free from everything except the wave itself. But space does not interfere with the normal radiation and propagation of waves. So, impedance is denoted as letter Z. It is an expression of the opposition that an electronic component, circuit, or system offers to alternating and or dielectric current. Impedance is a vector of two-dimensional quantity consisting of two independent scalar or one-dimensional phenomena, resistance and reactance. All material will oppose the flow of an alternating current. To some extent, this option is called impedance. It is analogous to resistance in DC circuits. Most commercial communications have antennas have an impedance of 50 ohms, while TV antennas and cables are usually 75 ohms. So reflection and VSWR. Um, Impedance causes mismatch and causes reflection and increased VSWR. Um, VSWR stands for voltage standing wave ratio. It is the Vmax over the V minimum voltage. So this is the waveform, sample of waveform of reflection and VSWR. So max impedance is also a maximum power transfer. The maximum power theorem, better known as the maximum power transfer theorem. It is an essential tool for ensuring successful system design. Put simply, this theorem states that the maximum power that can be transferred from source to load is 50%. So, which occurs when source impedance is exactly matched to the load of the impedance. The theorem is not as simple as it seems at first glance. However, it can be easily misunderstood. So in free space, um, the TEM or the transverse electromagnetic wave is thought as emanating from a dimensionless source. Mathematically, it is such a zero-dimensional source is obviously a point source. Moreover, the waves regarded as radiating uniformly in all directions from this point, consequently, we call such radiation point as isotropic source. The radiated energy is equal to what is the required the radiated energy of equal intensity is required by a sphere whose surface area is given by 4 pi r squared. So here, as we can see, it is the maximum power transfer. So the orientation of the E-field component of the TEM wave is called its polarization. Um, if the direction remains constant with time at a fixed point in space, the field is said to be linearly polarized. For wave propagation near the Earth's surface, the vertical, horizontal, and slant polarization are frequently used to denote linear polarization with appropriate orientations. So, next, the connectors. Most connectors have a well-defined gender. So, male connectors have an external housing or sleeve, frequently with an inner thread that is meant to surround the body of the female connector. They normally have a pin that inserts in the corresponding socket of the female connector, which has a housing threaded on the outer surface of two bayonet studs protruding from a cylinder. So beware of reverse polarity connectors in which the male has an inner socket and the female an inner pin. It is usually the cables have an male connectors on both ends, while radio frequency devices, um, example, transmitter and antennas, it has a female connectors. Lightning arrestors, directional couplers, and line through measuring devices may have both male and female connectors. So be sure that every male connector in your system mates with a female connector. So connectors comes in a huge variety of shapes, and sizes. In addition to standard types, connectors may be reverse polarity or gender swap, as we call, or reverse threaded. So as we can see here, these are the different types of male and female connectors. So as I said before, beware of the what you call this, yung akala mo male pero female. So makikita po natin dito na medyo nakakalito, confusing, slightly confusing when it comes to the male and female connectors. So beware of it. So adapters and pigtails. An adapter or adapter is a device that converts attributes of one electrical device or system to those of an otherwise incompatible device or system. Some modify power or signal attributes, while the others merely adapt the physical form of one connector to another. Great example for this is the fiber optic pigtail. Fiber optic pigtail is a fiber optic cable terminated with a factory installed connector on one end, leaving the other end terminated. Hence, the connector side can be linked to equipment and the other side melted with other optical fiber cables. So fiber optic pigtail are utilized to terminate fiber optic cables via fusion or mechanical splicing. So high quality pigtail cables are uh, coupled with correct fusion splicing practices. It offers the best performance possibility for fiber optic cable terminations. So, fiber optic pigtails are usually found in fiber optic management equipment like ODF, fiber terminal box, and distribution box. So, these are the uh, examples of adapters and pigtails. So, as we can see here, the first image, yeah, here. The first image here is the SMA female to and male. And this one, this adapter is called N male to N male. And this one, this is the N female to N female. And the fourth one is the SMA male to TNC male. This one is the UFL to RPTNC male pigtail adapter. And this one is the UFL to N male pigtail adapter. And the last one is the SMA male to N male female adapter. So adapter and pigtails are used to interconnect different kinds of cable of or devices. So isotropic antenna. So isotropic antenna, it is also known as the omnidirectional antenna. It emits the signal uniformly in all directions. In other words, at a distance from the antenna in any direction, the same transmitted signal power is the same. Although building a truly omnidirectional antenna is not feasible, this ideal antenna is frequently used excuse frequently used to simplify range estimations analysis as well as provide a reference point in comparing different types of antennas. So Um, Next. So, isotropic antenna radiates the energy fed into it equally in every direction in space, and it is a only an ideal model and cannot be built. So the next one is real world antennas. It is characterized by their ability to radiate their more strongly in some directions than in others. This is called directivity. When taking the efficiency of the antenna into an account, this preference for a direction of radiation is referred to as a gain. So, um, uh, take note that the antennas do not add power. They only direct available power in a particular direction. So, the gain of an antenna is measured in dBi or decibels, decibels relative to an isotropic radiator. The next one is the omnidirectional antenna. So, omnidirectional antenna, it spreads the signal evenly in every direction of the plane. So, um, best illustration dito yung parang yung water sprinkler. Yun yung antenna, tapos yung tubig yung pinaka signal niya. Directional antenna. A directional antenna forms a very narrow beam in a specific direction, and very little energy is directed elsewhere. So if the beam becomes much wider, we will have a sectorial antenna. So sectorial antenna, it spreads the signal in certain angle of the plane, for instance, of the 45 degrees, 60 degrees, and so forth. So often combined in a base station to provide 360-degree coverage, for instances, three sectors of 120 degrees each. So this is the illustration for a sectorial antenna. So directional versus omnidirectional. We have four types for this discussion. So the first one, all antennas have a specific use of case. In order to determine whether a directional or an omnidirectional antenna is best, you need to know that the basic functions of both. So the next one, an omnidirectional antenna radiates and receives the radio frequency energy equally, providing a 360-degree radiation pattern which allows the connectivity in all directions. So the next one is the directional antenna. It has a radius of around 45 to 90 degrees, while focusing the radio frequency energy in a required direction and limiting connectivity to that particular area. So this can help to overcome interference and multipath, providing better and more structured coverage. So the last one, the directional and omnidirectional antennas is in use within Wi-Fi AP application. So this is the great illustration for directional antenna. As we can see here, ayan, parang ito yung mas focused. Ito kasi, ito meron siyang isang area na mas pinagfo-focusan. Tapos parang hindi na lalagyan yung hindi na kakasagap yung ibang direction. While dito sa omnidirectional antenna, makikita po natin na lahat lahat 360 degrees nakakasagap ng signal. Hindi tulad dito sa directional antenna, meron lang siyang isang specific na what you call this, parang peripheral. Doon lang, ito lang direction na to. Pag sinet mo siya dito, ito lang yung direction na mabibigyan niya ng signal. Pero yung kabila, yung hindi sakop ng peripherals niya ay hindi mabibigyan ng signal. So dito sa omni antenna kasi, um, 360 degrees mabibigyan niya ng signal, lahat ng mabibigyan niya, malalagyan. So ito ganto po yung itsura ng omnidirectional antenna. While sa directional antenna naman, ito po, best example yung parabolic dish. As we can see here, isang direction lang yung mabibigyan niya ng signal. Yung omni directional, 360 degrees mabibigyan ng signal. So antenna features, marami tayong antenna features. A metallic structure that is used to transmit or capture radio electromagnetic signals is known as an antenna. These are available in different sizes as well as in shapes. The small sizes antennas can be found on the roofs. To watch televisions, yung mga basic antennas na makikita natin, yung what you call this, here. Wait. Yung mga normal na antennas na makikita natin sa roofs natin, yun yung best example ng mga small sizes antenna. Whereas the big ones are used to capturing signals using satellites. Yung mga big ones naman yung makikita natin sa outer space, sa NASA, sa DOST, yung mga malalaking satellites, yun yung mga big antennas. The antennas that scan, or as we known as space communications and navigation. So it mainly includes a particular antenna with ball shape that focuses signals at a particular end, known as a parabolic antenna. This kind of antenna allows both transmitting and capturing electromagnetic signals, which can move vertically and horizontally to transmit and capture the signal. So how to select an antenna? So for selecting the TV, selecting the TV right antenna for your particular television and location requires a number of things to be considered. So makikita sa pag-select ng TV antennas, unang factor na dapat i-consider mo yung open. Yung open, kung ilalagay mo ba sa roof, kailangan walang obstruction. The type of antenna, it is to be used for satellite or terrestrial, along with decisions about an internal or external antennas, antenna gains, and format, and many other things. So the next one is, when selecting an antenna, there is a huge variety of antennas from which to make a selection. So as I said before, there are many types of antennas. Merong ginagamit sa satellites, merong pang television, merong pang radio, merong pang what you call this, yes, yun, may pang radio, may pang television, at may pang satellite. So satellite or terrestrial. So the first decision to be made is whether the antenna is to be used for terrestrial or satellites DBS broadcasting. Satellite antennas typically require the use of a parabolic reflector or dish antenna. These need to be accurately aligned on the antenna and receive signals from the satellite, often at frequencies typically between 10.95 gigahertz to up to 12.75 gigahertz. So, terrestrial transmissions typically operate on frequencies in the UHF portion of the radio spectrum, although there are still some operating in the VHF portion or very high frequency portion of the spectrum in some countries. So the next one is next thing na dapat mong i-consider is kung indoor or outdoor ba. So one major consideration to think about when buying a TV antenna is whether the antenna should be internal or external. Internal antennas typically do not perform as well because of the walls of the building. It reduces the signal, and there are also reflections caused by objects on the building. So interference levels are also higher from fluorescent lights, electrical equipments, and many other items. So external antennas are able to pick up a much better signal, but they cost more to erect. The cables are longer. So the next factor that we need to consider when buying an antenna or selecting an antenna is the gain or the directivity. So one of the key parameters of any antenna is its gain. This is the increase in what may be termed its sensitivity in a particular direction. So the higher the gain, the higher its ability to pick up the weak signals. When the gain is increased, the antenna also becomes more directive, meaning that it must be more accurately directed towards the TV transmitter. But also, this has the effect of reducing the level of interference that might be received from the other directions. Excuse me. So the last factor that we need to consider when selecting an antennas is the TV amplifier. So in some areas, a TV antenna amplifier may be needed to boost the signal, because there are many different types of TV antenna booster amplifiers that are available. So often, enabling a single antenna to feed more than one television. So the next one is the bandwidth. So bandwidth is a measure of how much information a network can transfer. So the volume of data that can be transported varies, impacting how effectively a transmission medium such as an internet connection operates. The next one is the internet service providers, or as we all known as ISP, typically denoted bandwidth speeds in millions of bits per second, or BPS, megabits per second, or Mbps, and billions of BPS or gigabits per second. So generally speaking, the higher the bandwidth, the quicker a computer downloads information from the internet. So um, here in this section, we want to understand bandwidth. So what is bandwidth? It is a measure of how much information a network, a group of two or more devices that communicate between themselves can transfer. So when the data moves from A to B, just as water flows through pipes from a supply point to our faucets. So the volume that's transported, the bandwidth varies, impacting how effectively a transmission medium such as an internet connection operates. So ISPs, internet service providers, typically denoted bandwidth speeds in millions of bits of per seconds, as I've said before, Mbps, megabits per second, bps, billions, gigabits per second, Gbps. So yes, that is bandwidth. So what are the bandwidth requirements? The amount of bandwidth required to surf the web seamlessly depends on a task the user wishes to undertake. For instance, an instant messaging conversation may use 1,000 of bits or 1 kilobit per second in a bandwidth. A voice over conversation in which someone's voice transmit through computer connections, meanwhile, typically uses 56 kilobits per second or 56 kbps. So radiation pattern. Radiation pattern is defined as a mathematical function or a graphical representation of the far field. Example for R is equal to 2d squared over lambda, with d being the largest dimension of the antennas. So radiation properties of the antenna as a function of the direction of departure of the electromagnetic wave. A radiation pattern can represent several quantities such as gain, directivity, electric field, or radiation vector. Consequently, the terms gain pattern, electric field pattern, and radiation vector pattern are used respectively. So this is an example of a donut shape or toroidal radiation pattern. In this case, along the z-axis, which would correspond to the radiation directly overhead the antenna, there is a very little power transmitted. For example, in the x to the y plane or perpendicular to the z-axis, the radiation is maximum. These plots are very useful for visualizing which directions an antenna radiates. So, two-dimensional radiation patterns. A pattern is isotropic. If the radiation pattern is the same in all directions, antennas with isotropic radiation patterns don't exist in practice, but are sometimes discussed as a means of comparison with real antennas. So directional radiation pattern for the dish antennas. The third category of antennas are directional, which do not have a symmetry in the radiation pattern. These antennas typically have a single peak direction in the radiation pattern. So this is the direction where the bulk of the radiated power travels, and these antennas are very common. Examples of antenna with highly directional radiation patterns include the dish antenna and the slotted waveguide antenna. So it is a example of radiation pattern usage. So beam width. What is beam width? Beam width is the angle from which the majority of the antenna's power, as illustrated on the radiation pattern's main lobe, radiates. So it may be measured in the horizontal or vertical planes and is distance between 2 points where the power is less than half of the maximum. So analytical parameter. Planning antenna coverage in a given area, determining whether neighboring antennas will interfere with each other, assisting in improving the performance of communication links, devising the employment of networks within more than one environment, example indoor and outdoor, and the development of the network mobility. So half power beam width, or the HPW. An angle between the half power points of the main lobe as measured as -3 decibels. This is considered to be the part of the antenna output that has maximum consistency and utility, and is closely related to the gain of the antenna. If planning an antenna array, the HPBW will be the point where neighboring sectors cross over. So first null beam width, or FNBW. It is a degree of an angular separation from the main beam. It is found between the null points of the main lobe of the antenna's radiation pattern. This measurement can assist in assessment of antenna interference. So what is the relationship between bandwidth and gain? So when the direction and the radiation distance of an antenna are known, beam width can also be used to determine the signal strength expected for the antenna. Gain is concerned with both the power efficiency and directivity of the antenna, and therefore is also closely related to the beam width. Beam width and gain has an inverse relationship. Decreasing the antenna bandwidth will increase the gain. So this is because by reducing the beam width, power transfer will be increased in a particular section. So signal to noise ratio and beam width. As beam width relates closely to directivity and gain, alteration of beam width provides proportional changes in both these parameters. In addition, the signal to noise ratio, or SNR, the ratio of signal strength to unwanted interference, also changes accordingly. So if beam width is narrowed, gain and directivity will increase. This is also increases the signal to the noise ratio favorably. For this reason, the narrow beam width antennas are a prudent choice for long distance transmissions. So polarization. Polarization of an antenna is loosely defined as the direction of the electromagnetic fields produced by the antenna as energy radiates away from it. These directional fields determine the direction in which the energy moves away from or is received by an antenna. Vertical polarization. It refers to the oscillation of an antenna electrical field on the vertical plane, whereas horizontal polarization refers to the oscillation on the horizontal plane. So the next one is the slant polarization. It refers to an electrical field that oscillates at a 45-degree angle to a reference plane. GM's Engineering's LPA069, for example, it handled direction finding periodic antenna that can tilt to a 45-degree angle to receive slant horizontal or vertically polarized signals. So the next one is the circular polarization. So it refers to a radio wave that rotates as the signal propagates. When it rotates to the right, the polarization is referred to as the right hand circular polarization. So when it rotates to the left, it referred to as left-handed circular polarization. Many of GAM's multiband antennas products are circularly polarized. For example, the standard HSA 218 is also right-hand circular polarization. But JAM also makes an left-handed polarization version of the antenna. So, elliptical polarization. It refers to an electrical field that is propagated in an elliptical helix. Similar to circular polarization, elliptical polarization can either be right hand or the left hand. So, reciprocity. Antenna characteristics like gain, beam width, efficiency, polarization, and impedance are independent of the antennas used for either transmitting or receiving. Another way to state that this is that an antenna's transmitting and receiving characteristics are reciprocal. So wind load. As we can see, this is the great example of parabolic antenna with radome. And this one is the sector antenna. And this one is the parabolic grid antenna. So weather effects. As we can see here, the parabolic grid antenna, this is the normal look of the parabolic grid antenna. Well, this is the parabolic grid antenna covered by snow. So, antenna fundamentals. Antenna physical characteristics. The antenna's size and shape largely determines the frequencies it can handle and how it radiates electromagnetic waves. So, as we can see here, this is the thin dipole, biconical dipole. This is the loop. This is the helix. This is the log periodic. This is the parabolic dish reflector. This is the horn type. This is the microstrip. And this is the antenna array. So, wavelength. You may recall from physics that wavelength and frequency of an electromagnetic wave in free space are related by the speed of light. So, it denotes as the C is equals to frequency times lambda, or lambda is equals to C over frequency. Therefore, if a radio station is broadcasting at a frequency of 100 megahertz, the wavelength of its signal is given to 3 times 10 raised to 8 milliseconds. over 100 times 10 raised to 6 cycle per seconds is equals to 3 meters. So, antenna gain. Because an antenna is a passive device that the power radiated cannot be greater than the input power. So, the ability of an antenna is to focus the electromagnetic energy is defined by its gain. So, the gain of an antenna is measured of power transmitted relative to that transmitted by an isotropic source. Effective radiated power. So the effective radiated power or ERP is the gain of an antenna with respect to an isotropic radiator multiplied by its input power. ERP, input power antenna gain. For example, a highly directional antenna with a gain of 7 has an input power of 1 kilowatts. Its ERP is therefore 7 kilowatts. So, the dipole antenna. One of the most widely used antenna types is half-wave dipole. The half-wave dipole, also called as a doublet, is formally known as the Hertz antenna. Excuse. A dipole antenna is two pieces of wire, rod, or tubing that are 1/4 wavelength long at the operating resonant frequency. So this is the converting a transmission line into an antenna. And this is the illustration of dipole antenna. Actual antenna lengths. So a dipole resonates best when it is approximately 95% of the actual half wavelength length. So 1 feet is equals to 0.3048 meters, including that L feet is equals to 468 per frequency megahertz. So the dipole hung vertically is closest to an isotropic radiator. Bottom of dipole antenna should be at least half of a wavelength off to the ground. Next is the conical antenna. A common way to increase bandwidth is to use a version of the dipole antenna known as the conical antenna. The center radiation resistance of a conical antenna is much higher than the 73 ohms usually found when straight wire or tubing conductors are used. So the primary advantage of the conical antenna is their tremendous bandwidth. So they can maintain a constant impedance and gain over a 4:1 frequency range. So this is the conical the illustration of a conical antenna and variation. And this is the antenna beam width. So thank you. Thank you for listening. This is my final complete presentation for transmission media and antenna systems lecture and lab. Thank you.